Okay, so we will look at this week this string matching problems, right? Algorithms for string matching or pattern matching. So the problem, input, you are given a text and the pattern you know okay, so these are all from some where sigma is, let's say it's an ordered alphabet, it's for some reason a finite alphabet. So there are variations. You can ask, does the pattern exist in the text at all? How many occurrences are there? Find all occurrences. These are all the variations. Okay. So, example, if your text is something like this, and if your pattern is ABA, and when you say occurrence means it should be exactly, P0, whatever, P0 should match with whatever the starting point of the text is. Next one, there is no gaps. Okay. So, for example, here is ABA is occurring here. Here is an occurrence. These are the two occurrences. Okay. So, suppose I also change this to, and this is another occurrence. Yeah, so those are the three occurrences of the pattern in the text. Okay, so this is a problem. As I said, there are variations where you can ask how many occurrences, is there an, does P exist at all at T? Also, there are data structure variations where, which is a very important common application, is that I give you the text in advance. You should pre-process the text so that whenever the pattern comes, I should be able to answer whether the pattern exists in the text or not. Okay, so you can imagine all kinds of applications, right? Ranging from Google to text editors to biology applications, where all the time you're looking for, in your text editor, you are editing a file, you're checking, you search for some word in your text and you want to move across and find all occurrences. So the Google application would be something like you're given a text. I mean, here text is all websites together, and you pre-process it so that whenever I have a query, I should be able to answer fast all occurrences. Okay, where fast means something proportional to the size of the query. Right? I really don't want to spend time proportional to the size of the text. Okay, so we will see all variations of it, but for now it's a static thing for today. You're given a text and a pattern. I want to find all occurrences. Okay, and we'll look at various algorithms. A naive algorithm would be just move across this pattern in the text, aligning one by one. So you match, here is a match. So you found a match. After you found the match, you move it, shift it by one position, and then check for these patterns. Shift it by one position, find all occurrences. So how much time will that take? So M typically is much less than N, the pattern length. Yeah, how much time? Mn, right? Because this alignment, this naive algorithm, you take your pattern, so you're going to check for matches, that's like M time, and as soon as you're done, you're going to move it to the next. Just shift by one position, look for pattern. I mean, are there more clever methods than just start shifting from? Yes, of course, and we will see them later, but for now, the naive algorithm is order Mn, which is simply slide the pattern on the text by making character comparisons. Okay. Now, if the so there are we will get to a very efficient algorithm. If the alphabet size is very small, 4 or 5, the alphabet size, not right, then you can no actually if the pattern length is very small. So then in your text, here is my text. So think of A B A. I said it's actually ordered alphabet. So maybe A is 1, B is 2, and A is 1. I'm looking for 1 2 1 in this text 1 2 1 1 2 1 whatever. Think of this as a number, right? So you can look for this number, compare. So take the first 3 digits, consider them as a whole number, and compare whether the numbers are same. Okay. Assuming your pattern is small enough that this comparison is a constant time operation. Then once you compare and you find it matches, then you will output it. Otherwise, I have to align with these 3 characters. So this is a number. How do I compute this number? Right? It's the 3-digit number. It's a very easy way to compute the number from whatever this 3 digits. So let's actually do an example. Right? Suppose it's and my pattern is like 1 2 1. So I compare these 2 numbers, 2 3-digit numbers, and they don't match. Now I want to this number I know. Now I want to get this number. What is the value of this number, right? So what do? I my earlier number is there, divide by take a div of 300, right? So you get a remainder is 42, multiply by 10 and add 1. Right. So it's a constant time operation is what I want to say if these numbers are small. Okay. So so take this. This was my earlier number. Do a mod 300. Mod 300. I get the remainder 42. Multiply by 10 and add 1. I get this number, and then I compare these 2 numbers and continue. Right. Take a mod 400. I get the remainder 21. Multiply by 10 and add 5 and compare these numbers and so on. So what I want to say is that if this comparison of these 2 numbers is a constant time operation, then this would be like what? How much time will it take?
What's the difference between this and?
So here I am actually doing a character by character comparison. Okay, so that's what I mean. But here I'm thinking of this whole thing is a number, give it to my CPU and say compare these 2 numbers, 5-digit numbers. Okay, and I'm assuming that it's a constant time operation because this pattern length is so small. It's less than the machine word size or something like that. Okay. So I mean actually what I want to do is why I'm saying this is digress that there are lots of little heuristics one can do. Okay. We'll come back to this model and analyze algorithms, but there are all these little heuristics one can do. Then first given this pattern you compute this number, right, which is 1 into 10 power m plus 2 into 10 power m minus, assuming this is a decimal number, whatever the last thing, and this is some order m operation. After that, you are just doing some order n comparisons. So it's like an m plus n under all these assumptions that these numbers are small. Okay. Now there is a way around it. If the numbers are big, what you do is one of the standard tricks is to do mod something, some prime or something, so that the numbers become small when you do the mod, and then you will be able to compare. But there is a problem there that under mod these 2 numbers may be same, but they may not be originally same. So then you quickly check if they are different under mod, then you know that the numbers are different. If they are the same, then you go and verify whether they are the same. Okay, but all this will give you worst case if you care about it's like this kind of a running time. Okay, so but I just want to point out that there are all these kind of algorithms there. Okay, but here is a acute algorithm. Yeah. No, there are all these alignments across you need to worry about. Okay, you're saying you will divide it and then check for alignment here and then alignment here and then maybe. Yeah, I mean work it out. I haven't. I mean I don't know of an algorithm based on divide and conquer. But here is a cool application of something you have seen before. Okay, and I thought I will tell you that. So yeah, so here is a. Okay, so I'm going to, what is the kind of an algorithm running time I'm aiming for? I'm going to aim for something like n log m. So here is the observation. P exists in T starting at position Ti if summation Ti plus j minus Pj j equal to what? So these are numbers, right? Because I have said the character alphabet is 1, 2, 3 sigma. So all I am saying is the following, that here is my text and here is my pattern, and starting at some position I plus 1 up to I plus m minus 1, my text and the pattern match. Okay. So what does that mean? Then if you take the difference of these two numbers, add them all, what should I get? 0, right? Can I also say if and only if? No, right? Why? There could be some cancellations. If I want to say if and only if, what should I do? Mod or square. Okay. So let's write this. If and only if summation this is equal to 0. Okay. So all the positions I on for which P exists in T should satisfy this condition. So now I want to look, find such I, all such I, right? That's our goal. How do I do it? Let's see. So first, let me actually aim for an n log n algorithm, then I'll improve it. So I'm going to write this as P exists in T starting at position Ti if and only if, let's expand this out, right? This is just numbers anyway. Summation j equal to 0 to m minus 1 Pj square plus summation j equal to 0 to m minus 1 Ti plus j square minus okay. So I don't know the I. Our goal is to find all such I for which this happens. Okay. So let's see how much time we need to compute these for a fixed I, right? Or for all I rather. Well, how much time? This is independent of I. This is independent of text. It's just a function of the pattern. So I can compute them in order m time, right? Sum of the squares of the Pi values. So this is order m. Well, how much time does this take? For a particular I, this is also some m terms, I am squares adding them. But if I want to do it for all I, how much time will it take? N time, how? Exactly, right. Do you see that? Because I have for a fixed I, this is my text and I am computing the sum of the squares of these numbers. So, that is like m terms, order m. And then what is this saying? Just move the next I, right? I plus j plus 1 square to I plus 1 plus whatever. So, that is basically saying I want the sum of the squares of these guys. So, subtract this and add this square, subtract this square. So, this also can be computed in order n for all I, not just for one I. Now, let us look at this. How much time does it take to compute this, right? Because naively there are something like m terms for a fixed I. So, it is like an mn kind of a thing, but does that ring a bell? Convolution, yes, polynomial multiplication. So, what I am going to do is to set up two polynomials. And what are these polynomials? So, t of x is t0 plus t1x, x is some variable and p of x is p0 x power n plus p1 x power n plus 1, no, n minus 1. So, let us suppose I write this polynomial. Okay. So, this is just given the text, I know the t0 to tn minus 1, I write this polynomial, and similarly I know the pattern, I write this polynomial. Okay. Each of degree at most n minus 1, actually this stops at n minus degree n, it goes up to n, yeah. You want the n, yeah, okay, fine. Sure. Okay, so then what is this term? Let us see, summation, right. This is what I want to compute. Then let us look at the coefficient of x power n plus I in Tx times Px, the product. In the product, how do I get n plus x n plus I, because this is starting at, well, okay. Yeah, so I am going to match it with this. So, I pick some jth term from here. So, I get x power n minus j, and then here I should get j plus I, right. The j should cancel out and I get j plus I. So, to get j plus I, it is basically t I plus j, sum this over all j. How far should I go with j? Well, p anyway goes only up to m minus 1. Okay. So, this is cool. And how much time does it take to compute this product? We have seen that. This is using this fast Fourier transform, complex nth roots of unity, evaluate them, multiply product and all that. If two n degree polynomials, we can multiply them. The naive algorithm will take n square time, and what we saw was it takes n log n time. Okay. So, we can compute this product polynomial in order n log n time. So, my overall running time, remember when I compute this product, so how much time I have spent to compute this summation square, I get order m. To compute the ti plus j square for every I, it takes me order n, and to compute this product takes me n log n. So, that is my running time, and I claim that that is good enough. Now, to verify this term is sitting there with me, this is sitting there, and I have this product polynomial sitting there, and I go and find the coefficient of x power n plus I, and that gives me this, and take 2 times, subtract, check whether it's 0, do it for every I, and you can find wherever, whatever I that satisfies this, you get the pattern existing in the text. Okay. So, this is a cool application of FFT. Okay. So, that is one of the reasons I want to say this. And this is not really mentioned in the context of string matching, because we are going to give a much better algorithm. We will actually give an m plus n algorithm tomorrow. So, but it is nice to know, because this has also interesting applications for approximate string matching, right. So, you can talk about not exact alignment, maybe I have some don't care symbols in the pattern and in the text, and I want to match them, or I want to allow a few mismatches. All this can be, you can take this kind of an equation, and if when you allow mismatches, put in something else, and some other thing will come out, and for computing something like this, you set up 2 polynomials, compute the product, and you can get them. Okay. So, that is actually a more efficient algorithm than any other way of doing it for approximate string matching. For exact string matching, we will improve this anyway, but okay. So, I just wanted to mention as a cool application of FFT, right. So, computing product of 2 polynomials of each of degree n, we saw that can be done in n log n time. All right. So, let us go on to more algorithms. So, suppose I give you the pattern in advance. Okay. Like I said, if you want to talk in terms of the data structure question, there are 2 variations. I give the text in advance, and you search for a lot of patterns. This is the common variation, right, in your text editor or Google or any other application. Text, you pre-process it, and then on that text I am asking for a lot of pattern. But let us look at the other variation first. Okay. Suppose I give you the pattern first. I want you to pre-process it and be able to find all strings containing that pattern. Okay. So, let us do an example. Yeah. Sorry, can you say again? Yeah. Yeah. Okay. Yes. So, this was one of my assumptions, right? Right. There are 2 answers to this. One, we will see other algorithms which do not require this addition and subtraction. The other thing is, you can take your character and map it to some numbers 1 to alpha, sigma, and then you can map it back whenever you want, kind of thing. So, yeah, okay. So, what you are saying is that these are not numbers, but some a and a b, and what does it mean by multiplying this a and b? Good question. So, this algorithm, this method works whenever you can, you have an ordering and numbering of the alphabet. Yeah, but we will say other algorithms. Okay. So, here is the question. So, suppose I give you this pattern A B A B. Okay. This is something you would have seen it in other courses. I want to process it somehow and be able to quickly find all strings containing P, or I mean, what is sort of a machine you will construct to detect this is my question. Another thing is, given T, you want to find whether T contains P, right. That is our original problem. Whether T contains P or all occurrences of P in T and things like that. But I give you the pattern in advance, and text is coming one by one. So, what sort of, how do you pre-process the pattern? computing number. All strings containing AB, AB. Do you know some nice property of this set of all strings? Exactly. So, what would you construct? A DFA, a deterministic finite automaton, right? So, let us see. So, given a pattern, so do you guys know what a finite automaton is? I mean, in your discrete math or theory of computing course? No? Okay, so let me briefly describe what it is, right? So, it is a machine, think of it. So, a DFA, it's called deterministic finite automata, is actually a 5 tuple, okay. It's actually formally defined as a 5 tuple, where Q is a set of states, sigma is your alphabet, S is the starting state, and F is the set of final states. Okay. And delta is a transition function. So, what does it do? It takes, you are in some state and you get a character. So, it is a deterministic finite automata. So, you are in a state and you get a character, next character in your text, and this will tell you what is the state you go to. Okay, delta is a function from Q cross sigma to Q. Okay, so, I will draw a picture, and that is a much better way of seeing how a deterministic finite automaton looks like. So, for example, here is a deterministic finite automata. It has exactly 2 states. If I see an A, I go here, and if I say a B, I stay here. So, my sigma is AB, and if I say a B, I go here, and if I see any. So, I arbitrarily drew a finite automata and say this is my S and this is my F. Okay. So, a deterministic finite automata can be pictorially described like this, which tells you what are the states. It's a diagram like this. This is a starting state, right? I need an S, and you have a collection of final states. In this case, I am saying this is the final state, and the transition function is defined in the picture like this. If you are in state, so transition function takes a state and a character, and it tells you which state to go to, right. So, if you are in state 1 and you see a character A, it says go to state 2. If you are in 1 and you see a B, you stay in 1, and if you are in state 2, you see an A, stay here. If you are in 2 and you see a B, you go here. Now, there is a language accepted by this machine. Let us call this as a finite automaton, is all strings such that X reaches F at the end, right. So, you process your string X, look at character starting from starting state, look at character by character and follow the transition, and after reading X, if you are in F, then I know that X is accepted by this machine. So, X belongs to this language, otherwise it does not. Okay. So, now I drew an arbitrary DFA. Does anyone know what language it accepts? Strings? ending with A. Okay. So, one answer is all strings ending with A. Yeah, okay. I think that sounds right. So, the language, so if this is my M, the language accepted by M is all strings in, because this is my final state. I didn't think that a machine will have some meaningful language. Okay, so is that clear what a deterministic finite automaton is and what is a language accepted by the machine, right? Deterministic finite automaton, think of it like a picture. There is a start state, there is a set of final states, and there is a transition function. And the way you use the machine is to, given a string, you want to know whether the machine is accepted by the string. Start from the start state, process each character at a time, and see at the end which state you belong to. Okay. So, now let us say if I want to construct a machine M such that the language accepted by the machine is all strings containing AB, right? Like that is my pattern, and I want to, pattern is given to you in advance, pre-process it, construct a finite automaton such that any string that contains AB, that particular pattern, when you run it through your machine, it will reach an accepting state. In fact, yeah, not just that. So now, I mean, yeah, and you can also tweak it to output all starting positions of the pattern in the text, right. So, every time when you reach the final state, when you reach one of these final states, you know that you got your pattern in the text, but you are continuing to process the text anyway. So, you know how, when, where the text started, and you continue to process it, and you will see all occurrences of the text. Okay. So, let us see how the DFA would look like. Because the advantage of this is that if so only the pattern is given to you, you spend time proportional to some function of the pattern to build this DFA, and after that, how much time does it take to? We'll look at an example and see. Okay, so we'll see it for okay. I'm saying this is slightly different from being able to find all occurrences of AB. Okay, first we'll look at this and then we'll come back to how to do the other one, right. So, if I want to find all strings containing AB, here is a simple way. So, I start, this is my starting state. If I see a I go to state number 1. If I see a B, I go to A3, then I see a B, I go to state number 4, and I call this as the final state. Okay. So, now when I want to process the text, this is not a complete description of the DFA yet, because you haven't told me if I am in 1, if you see a where should I go? That is not completely. So, the transition function is not complete, but I have given some partial thing, right. So, let us fill it up. So, if I am in S starting state and I see a B, what should I do? Stay there, right, because I am looking for AB. So, I stay there. Okay, I have seen an A, and here I see an A, what should I do? Stay there. Why? Let us see. Go back to S. Okay, there are two choices. Should I go back to S or should I stay there, right? Okay, so the suggestion seems to be to stay there. If I see an A, so more formally we will get to how do I construct this machine for the pattern, and more the crucial thing is the transition function. Where should I go? And at this point we are working on this example. Let's say, see, the reason you stay there is that so far you have seen one character of the pattern, and if you see A, then you can treat that as the character of the pattern you have seen. So you stay there. Now, more formally, what is it and how do I construct the DFA? We'll get to that later. Okay. So now I'm here. If I see a I go here. If I see a B, what should I do? Go back to start state, right? Because what have I seen? I've seen A, B, and then I'm seeing a B. Start all over again because we have not seen any part of the pattern. So you go to S. Now you have seen A, B, A. Now you are seeing A here. What should I do? Okay, so right, how much of the pattern have you seen? Well, you have seen A, B, A, but this A could be the starting alignment of the pattern. So you go here. Okay, so now what should I do if I see an A or a B here? Stay there. If I care only about strings containing AB, all languages, then stay there. Okay, this is the difference I was pointing out. So if I stay there AB, that means that the moment I find one pattern AB, I get there and I say, this is a good string for me. I found the pattern. But if I want to find all occurrences of the pattern, then I don't stay there. I do something else, right? So that's the difference I was pointing out. To answer this is good enough here. But if I want to find all occurrences of the pattern, then if I see an A here, then let's see how much of the pattern I have seen so far. Well, I've seen an AB, and so I reached this state and I sort of mark it, right? Output the position 4 positions before as one starting point of the one occurrence of the pattern. But now I have seen, now this could be an occurrence of another overlapping occurrence of the pattern, right? AB. So where should I go? If I have seen AB, I should go here. To ABA, it's not just AB. You've seen AB and an A as well, right? So you've seen A, B, and this A. So ABA will take me to position 3. And if I see a B here, it's an ABB, doesn't mean anything. So I start all over again to go to S. Okay, so that's the deal. So this is the difference I was pointing out about Nidhi, that strings are containing ABAB, then you can just stop here and look at all ABAB. But if I want to find all occurrences of the pattern, then even here I need to worry about where should I go. Okay. Oh, every time you reach 4, you got one occurrence. And more importantly, how do I know where the pattern occurred? Because so how am I going to use the machine? Some text comes, right? T0, T1, Tn minus 1. So take the text and run it on this. So start from S, depending on whatever my transition function tells me, I stay in that appropriate state. The moment I reach 4, let's say I reach state 4 for T25. That means that 22, 23, 24, 25 is my pattern. T22, 23, 24. Because I've reached here, that means that exactly the previous 4 positions form a pattern. So I know that here is one occurrence starting at T22. I can output that and continue. Every time when I reach This state 4, I know that I found one occurrence, I know where the occurrence is. So, so I process my entire text this way. So, the good thing is after I construct the DFA, we will come back to how much time it takes, how do I construct it, we will discuss that. But it is just a function of m, the pattern length. After that, it is an order n time, right? Because I take my text and run it through the machine, and every time when I reach the final state, I know I have found an occurrence, output. So, it is much better than whatever algorithms we have seen, if this f of m is pretty reasonable, and the pattern size is expected to be much smaller anyway. So, that is okay. So, let us see in general, given a pattern, how do I construct this DFA, right? What are the states, and what are the states is fairly obvious looking at the way we did it, but more importantly, how do I get the transition function, and if you are at a state, where should I go? How do you figure that out? Yeah. So, constructing DFA for some pattern which is, let us say, P0, P1. First, the way exactly the way we did, we say, okay, here is my starting state. If you see a P0, you go to state 1. If you see P1, you go to state 2. And if you see Pm minus 1, you go to m minus 1. And this is my final state. I mean, this is where I start capturing the occurrence of the pattern. Now, I have to figure out, if I say P0, I go to 1. So, if you go to Pmi, oh, maybe m, yeah. And that is the final state. So, now more important thing is, if I am here, or if I am 0 and I find something else, where should I go, right? So, let us put in some notation and talk about it.
From the start.
Largest.
You went to the state which has the largest substring from the start.
Largest substring, or starting from beginning. Yes. So, largest prefix.
Yeah.
Yeah. Okay. So, that is the notation I am going to talk about. Yeah. So, okay. So, let us use this notation sigma of x, where x is some string. Is the largest suffix of x that is also a prefix of x. Right? You understand what suffix and prefix is? Given a string, suffix is the last so many characters. Right? Everything, the last character alone is a suffix, last 2 characters is a suffix, last 3 characters is a suffix, those are the things. And prefix is starting from the beginning. So, if my string is, if this is my string, then A is a prefix, AB is a prefix, ABA is a prefix, ABAA is a prefix, and so on, right? And suffixes would be starting at the end, right? So, it's B is a suffix, BB is a suffix, ABB is a suffix, and so on. And this is a suffix, this is a suffix. So, here is my, so to construct this DFA, you know the number of states, Okay, this is how I am building it. Number of states is m plus 1. Okay, alphabet we know the starting state and we know the final state. The only thing I have to now tell you to complete the description is what? The transition function, right? Because these are the states and these are starting state, this is the final state. So, only thing I have to tell you, if I am in this state, if I see this character, where should I go? That is exactly the transition function, right. And here it is. So, it is if I am in state I, right, 0 2, and if I see character A, where should I go? So, let us again put some. So, my P is P0, P1 up to Pm minus 1. So, let us define Pi as P0 to Pi. Okay, maybe I should define my P as so let's maybe I'll define this P as P1 to Pm and Pi is P0 P1 to Pi. Right, this is a prefix. Starting from the first position, go up to the ith position. That prefix is what I am calling it as Pi. So here is my claim. It is simply sigma of Pi A. I should not even use A. Let me use, because A is, I've been using A for a fixed character. So let's say some X. And remember, the sigma definition is that, okay, let's actually get a feel for the sigma, right? Sigma of ABA is what? More precisely, the length of. So, what I am talking about is the largest suffix which is also a prefix. Okay. So, a suffix A is a suffix and A is also a prefix. So, length of the largest one suffix which is also a prefix is A and its length is 1. Can I increase it to more? So, if you look at this suffix BA, no, that is not a prefix. Of course, ABA is a prefix and a suffix. So, maybe I should say largest. Yeah, that's okay, fine. Yeah, in this case 3, because if I do not say proper suffix, then the whole thing is the entire suffix is also a prefix. So, it is a whole thing. Okay. But actually I do not want to say proper. Yes, so in this case it is 3, but yeah. So, here is my definition of the transition function. Let us see why that is true, okay, based on our understanding of what these PIs are there, right. So, suppose I am in state PI. From this figure, what does that mean? I have seen I characters of the pattern, right. I have matched I characters of the pattern, that is what it is, right. So, I am in state I means that in my thing I have seen P1, P2 up to Pi in my text somewhere. This is my text. In the text, when I am processing, I matched these guys, right, because that is how I will get to position i's. Because how do I get to I? Because until I see some P0, I stay here or something what I do. Then I go to P0, I see P1 and see Pi and I get here. Sorry, Pi or Pi minus 1. No, okay. I think I started my pattern with 1. So let me. Yeah, so this is I means this I've seen pi. Yeah, I've seen I positions. So now I'm next character is coming, which is x. So if this x happens to be pi plus 1, then I know what am I saying? Take this entire prefix pi and add this x and see what is the largest prefix which is also a suffix.
So actually it should be tracking.
Because that will always be cardinal in length of x.
So if the P we started with in this example it was ABAB. If it was ABBA, then for this length ABA, we are kind of making it to
No, so what, let's see what is it. Length of the largest suffix of x, that is a prefix of p. No, I think this is what I want to say. Prefix of the pattern. Okay, so somehow it is connected to pattern, whereas this is an arbitrary x. Given an arbitrary string x, I look at the largest suffix of this, which is a prefix of the pattern. Does that look okay now? Then what I am saying is, yeah, so even here it may not be 3, because depending on what my pattern is, if my pattern is some a b b a, then sigma of x would be what is the largest suffix which is a prefix of the pattern. In this case it will be 1, because 2, right, no 1, because it is just this suffix a which is a prefix of the pattern. Okay, so yes, so it's not just about x, I'm connecting with the pattern p. So it's all, everything is defined with respect to this pattern p. So you have matched up to this point and look at x. If x happens to be pi plus 1, then I know that the largest suffix, which is a prefix of the pattern, is actually I plus 1. So I will actually go to I plus first state. That's exactly what I should do. If not, if it is something else, then I look at the large, how much of the pattern have I seen including x. That is basically the largest suffix of the pattern, which also happens to be the prefix of the largest suffix of this text, not the pattern, largest suffix of this text, pi concatenated with x. What is the largest suffix which also happens to be prefix of the pattern? Take that number and you go there, because that tells you how much I have seen. So then you will go to appropriate position. Here it depends on having seen this and this character, what is the largest suffix which is a prefix of the pattern we have seen. Okay. So one can formally prove this, but I am not going to do it. So having defined this, now let us compute how much time it takes to compute this transition. So what I'm so here is my, so let's come back to the sigma definition, right? Given any arbitrary string x, sigma of x is the, what is the largest suffix which is a prefix of my given pattern. So the sigma is always with respect to p, the fixed pattern. So what is the largest suffix which happens to be the prefix of my pattern, right? So this, if this is my pattern, then this is the largest suffix. So whatever that length is sigma x. So now what I am saying is, if I am in state I and I see a symbol x, where should I go? That is my question. If I am in symbol I, the invariant which we can prove by induction is that I have matched P1, P2 up to Pi in my text. When I am processing my text, somewhere I have matched P1, P2, Pi, and the next character coming is x in the text, right? Because how is this machine used? The machine is used to process a text string. So I process it, I come up to this point and I know I have seen this, and I am seeing an x, and where should I go? I have to set up my DFA appropriately. If x happens to be pi plus 1, the next pattern, then this definition tells me sigma of pi, what is the largest suffix of this, because that is what pix is. What is the largest suffix that also happens to be the prefix of the pattern? Well, that is the entire pattern. So, largest suffix is I plus 1. So, I go to the I plus first state. But if this is not pi plus 1, but it is something else, there is a mismatch, then I take this entire, because I have seen this much, out of this, how much of the pattern have I already seen in the suffix, and that is exactly that sigma tells you what is the largest suffix that happens to be the prefix of the pattern, and that number tells me that that is the state you should go to, because that means because you have processed and aligned and got something so many so far. So, you go to the next state and then continue exactly the way we did, right. This is a the instantiation of all this definition, or think of it as a formal way of how we constructed this. So, now let us see how much time it takes to construct the DFA very naively. Well, I mean, I have actually told you how to construct the DFA. So, let us time for constructing. You set up the states, you have this state 0, P1, state 1, M, this is the final state. The only thing is how much time does it need to compute this number, that is all I need, right. So, if I am in state I, so very naively what do I do? So, for every x, so let us fix I and x, right. How much time does it need to compute this is what I care. So, what is this? This is P1, P2, Pi followed by x, and I want to know what is the largest suffix, which is a prefix of the pattern. Right. Very naively you can say try one at a time. So, take this suffix and see whether that is a prefix. Yes, if it is no, then you are already done, move on. If this suffix is a prefix of the pattern, try this and compare with this, otherwise try this and compare with this. So, you are going to check some I plus 1 suffixes, right. This is a suffix, there are I plus 1 suffixes, and for each one you are going to test with the with pattern. So, even if you just give yourself I time for each one of them, something like I square, yeah, that is like I square, yeah, I square time to compute this for a fixed I and a fixed x. At the moment I am not going to worry about it. And how many different characters are there? Sigma different characters, that is my alphabet symbol. So, I multiply by, so multiply by sigma, how many different I is there? Some m of them. So, overall I am going to say m cube sigma time, because for a fixed I and a fixed alphabet I will spend I square, I am going to even make it m square. Okay. Different alphabets, sigma different, because for every state I have to look at the where all would I go for every character in the alphabet. So, that is I multiply by sigma. And how many different states are there? M different states. So, that is m cube sigma to construct the DFA, and after that order n to process your text, because for every I need to know where all different characters are possible, right? I need to know where should I go for if I get character A, if I get a character B, character C, character D. So every character in my alphabet I should know where do I go. So that's this X, right? If I am at state I, X is coming from sigma, right? So for every value of X, I have to, there is a time involved in it.
So that is somewhere incorporated in that I square time that you said.
No, when I put in an X, that alphabet, this alphabet is attached here when I am checking for all these prefixes. So when you change the alphabet, that different alphabet will come here, and then I will check for suffixes. Yeah. Yeah. Yeah, that's what I'm going through now. So what I'm saying is, all I'm saying is that this computation order m square for a fixed I and a fixed X in sigma. That's all I'm saying. For a fixed I and a fixed X, I want to tell you that it takes m square time. Now, how many different i's are there? Well, I is the number of states, which is m plus 1. So, I multiply it by m, that gives me an n cubed. How many different x's are there? Sigma different x's are there, so I multiply by sigma. Okay, now why is this time? That's very easy. So, what is that? Look at the definition. If you fix an I and an x, what is this? This is saying look at pi x, which is what? P1.
Function sigma is sigma is different, right?
Ah, okay.
So if this is cardinal.
This is alphabet size. Yes. Yeah. Sorry, that this sigma. Also, I called it a sigma. Okay, is that the confusion? Okay. Yeah. Sigma is a number which is the size of the alphabet, and that function is sigma x. At this point, I don't want to change any of them because I think they are somewhat standard. So what is the sigma saying? Look at P1, P2, Pi, and x, and look at my this is Pix, and my pattern is P1, P2 up to Pm. And the claim is that look at the largest suffix of this, which also happens to be a prefix of the pattern. There are I plus 1 possible suffixes. For each one of them, take that suffix and match it with your pattern, and one by one each character comparison, and see how much time it takes, right. So, that is I plus 1 into I. So, something like I square, which I upper bounded by m square. That's all. Okay. So, net for our original problem which we started out with, okay, let me be more specific like this to avoid overloading sigma. For my original problem, this is my running time, which is pretty reasonable because m is much smaller compared to n. So, m cubed is not such a problem, but there are faster ways of constructing this automaton, and Knuth Morris Pratt came up with even clever way of okay. So, this is the next algorithm we will see. I may not do it today, I will do it tomorrow or next time Friday, but I will set it up. This what they did is something like a DFA. This is some prefix function which they computed in order m time, and then something like running our text. So we'll look at this next time. I mean, so just to give you an idea how it works is that this is what I actually hinted in my original naive algorithm description. So I have a text. Let's say it's some AB, and I have so I've tried to, I matched A here, B here, and A here, and then this was a mismatch. So the naive algorithm would say, okay, start, just shift it by a distance of 1 and start comparing A with this. That's what the naive algorithm will do. Once you see a mismatch, you shift the pattern one character and then compare. But looking at our pattern, we know that this, so we know that this is not A. So why would I compare it, right? Somehow, so that's the prefix. From the pattern, you do some pre-computation, which tells you that if there is a mismatch, how much shift you have to do, right? So if I matched all this point, there is a mismatch here, then I know that this is A, this is B, this is A, right? So the mismatch is here. It's sort of like the DFA computation, which tells you how much to shift, but somehow they do it without the dependence on sigma. It just uses the fact that there is a mismatch. Okay. Yeah, so we will formally see this next time. What I want to do in the next 15 minutes is look at the other case, the important case where I give you the text in advance and I allow you to pre-process it, and I want fast pattern matching. Okay. That is a very nice data, very powerful data, very simple but very powerful data structure, which does it very efficiently. Okay. So the problem is, okay, so this KMP we will look at on Friday. Given text T, pre-process it so that
Is the pattern size known or is that arbitrary?
arbitrary, nothing is known, no size, nothing. So that given P, occurrence, or rather all occurrences of P can be checked and I really want to compute this in order P time. Right? This is sort of the reverse process of what we did for DFA. Given a pattern, I allowed you to pre-process it, you constructed a DFA, and then when the text comes, you run it in order n time, you got the whether the pattern is all occurrences of the pattern. Here it's the other way where I give you the text. This is a common application, right? Even in your editor, you have this huge file which you are trying to edit. I give you the text, pre-process it. Now I ask for various patterns, and at that time, the occurrence of P or all occurrences, I want to be able to check in order P time, size of P time, right? Google applications, all of this belong to this kind of a category, right? So the data structure is actually what is called a suffix tree. It's very simple actually, but it's very powerful in the sense not just for string matching. You can have multiple different texts, multiple different patterns, and you can ask for some longest common substring of all these texts, various kind of clever queries. suffix trees can answer them. Okay. So let me define a trie for a set of strings. Okay, not suffix tree, but so you're given some set of strings. Let me draw an example. Suppose these are the set of strings and I want to build this data structure, the trie, right? It's called, it looks like this. I mean, I can formally define it. It's a rooted tree and it looks like, and ABC would look like. So let me give some number 1, 2, 3, 4. ABA will be 1, ABC will be 4. So it's more formally it's just a rooted tree. Every leaf corresponds to a string in that set, and corresponds to means what? So every edge has a label. Character label. And the concatenation of labels from root to a leaf gives the string corresponding to the leaf. And the more important thing is that no two children or no two edges out of a node has the same label. Okay, right? In so many different words, basically I defined formally how the tree looks like. In other words, I can't have two A's coming out of one node. If you need to use the same A, that's all it's saying. So now if, okay, so is it completely defined because it's a rooted tree and every edge out of the node has a label, character label, and no two edges out of the same node has the same label. A leaf corresponds to a string, and the precise string is you just concatenate the root to leaf path, and that corresponds to the string. So in this tree now, if I want to know whether there is a string that exists in the text, how much time will it take? Right? Given a trie for S, suppose there is some x in sigma star and I ask is x in S. How do I find this? How much time does it take? Length of x, right? So what do? I start from root, take the first character of x and see is there an edge going out of that node. If it's not there, good, x is not there. If it's there, I follow through, take the next character, follow through. The good thing is there is only, if at all there is an edge out of a node, there is only one with that character. Yeah, so I mean, formal implementation of this, you know, you may need an array of characters with some empty pointers coming out of this node and so on. So, the time it will take you is order length of x. Okay.
These set of strings are basically the substance.
Which set of
For the main string, like the
at this point, I just said try for some arbitrary set. I haven't told you what suffix tree, and that's what you are getting to. Yeah.
length of the string or length of the largest string.
No, length of that string, because
Not there,
then I stop, right, and I can say no, the string doesn't exist.
and if it was there, then I will let it.
If it's so, if my x is BBA, let's say. So what do? I take the first character and follow through and say, oh, maybe x is here. If x is there, it has to be a leaf out of it. Then I come here and B is not there. End of it, x is not there. If it's there, I follow through, and then I follow through A and
If it doesn't stop at the leaf string,
yeah. Okay, so there is one question is what if one of these strings is a substring of the other, right? So, for example, if I want to store also BA, right, then what do you do? Okay, that's a problem. So, for now, let's assume that set of string, no string in S is a substring of other.
How much time would it take at each node of the tree? Like, is it
Constant time. So, that's an implementation detail which I glossed over, that depends how do you represent this. So, at this node, I may have, so if I may have kernel sigma many pointers. Some of them may be empty. Then you follow through and say, okay, character, there is a C which is empty, so there is no C out of it. So, if I implement it that way, then it is constant time to navigate and see whether there is character C. But there are other implementations. Okay, so now getting to what you are trying to tell me, right? So, what we are saying, so what is the suffix tree? Okay, so this is the problem we are trying to address. A suffix tree of a text is a trie for all suffixes of the text. Not quite T, but I will come to that.
here even if it stops in the middle, it's fine.
It's not. It's the same kind of problem we need to do. So, what I will do is I will add a dummy character dollar and look at all suffixes of T dollar. Then no suffix is a substring of the other. So, I can handle that. Okay. So, let me give an example. So, if so, this is the problem. I am going to erase that. Okay, but let's see. So, you are given a text T, let's say B, A, B, C. I add a dollar and I look at all the suffixes. What are the suffixes here? Dollar is a suffix, C dollar, BC dollar. And these are the suffixes. Now I construct a suffix, a trie for this set of strings. So that trie will look like this, dollar. So 1, 2, 3, 4, 5, 6. So let's say this is position 6, 5, 4, 3, 2, 1. C dollar, and I'm going to say position 5. And then I don't want another B or C. So, this B will have a branch to position 2. Okay, so I omitted all that. One thing I have not really told you is how to construct this tree given this character. Let's for the moment not worry about it. So, what I have is each leaf giving me a suffix of the text starting with the starting position. Leaf number is the starting position of the suffix. Which means if you read the root to leaf, that gives you the entire suffix. Okay, and with all the shared things, it's a try, no two different edges have the same character and all that kind of thing. Now, here is a non-trivial observation. Actually, it's a trivial observation. What is my problem? I want to know P exists in T, right? That's the problem. Given a pattern, I want to know whether it exists in the text. If and only if P is a prefix of some suffix of T. Okay, not saying really much because what is it saying? Here is my text, and suppose P exists here, then P, this occurrence of P is actually a prefix of this suffix, right? So, you can actually answer something even stronger. Not only X is in S, you can even answer, is X a prefix of some strings in S, right? Because it's same algorithm will work. You follow through an X and you stop at some point, then you know that X is a prefix of some string in S, right? So, it's the same thing. So, if I have this suffix tree and I want to find all occurrences or an occurrence of P in T, construct the suffix tree, right? All the suffixes. Okay, and maybe we will look at this next time. The reason we add delta is that every suffix ends in a leaf. Okay, because no suffix is a substring of the other. So, to know whether P exists in T, all I need to know is whether P is a prefix of some suffix in the text. How do I do it? Well, run through P in this tree. Look at character by character of P. You don't even have to go all the way up to a leaf. So, so you want to know whether AB occurrence P is AB, and I follow through A, yes, and then I follow through B, there will be a B somewhere, and you will stop here. That means AB occurs in the text. If I want to know all occurrences, how many occurrences, even that information is there. How do I know all the occurrences? All the exact. So you follow through your pattern in the suffix tree, and suppose you end up in an internal node. Then you look at the subtree of that node, right? And look at all the leaves. They correspond to all occurrences of AB because AB is a prefix of all these suffixes. That means that is the number of occurrences of AB, where all it's appearing, all that is there. Okay. Now, so you can actually check if P occurs in order P time, but how much time does it take to find all occurrences, and how does the tree look like? These are things let's deal with it next time. Okay. So, one of the problems with suffix tree is that it consumes a lot of space, but there are ways to optimize on the space and answer this question and more general questions in very efficiently. Are suffix trees unique? Yes, they are, because the try is unique. For try for a set of strings is unique. There's only one way. I mean, you can the way we construct it. That's the only way. Okay, so next time we will start with this definition of suffix tree, see more applications of it, and then we will get to KMP algorithm for m plus n time matching. Okay.